This episode is sponsored by Brilliant. Hello, welcome to Up and Atom. I'm Jade. The three-body problem is one of those rare problems in physics that changed our understanding of the universe. And I'm not exaggerating for views. It really was revolutionary. It goes like this. Imagine you have three masses, or bodies, in space, all affected by each other's gravitational pull. If you know each of their position and momentum at the present time, predict their position and momentum for some future time. That's it. Sounds simple, right? We know all of Newton's laws of motion, and we know Newton's law of gravitation. But despite how simple it sounds, this question uprooted over 100 years of physics, caused a chasm in the landscape of science, and shone a light on the limits of what we as humans can know. How on earth did a simple question about planets do all of this? To appreciate the gravity of the three-body problem, we need to go back to 1889. The story starts with a birthday. The King of Sweden, Oscar II, was turning 60, and to celebrate, he held a maths competition. He was wild like that. The big question was, is our solar system stable? Will the planets continue to orbit the sun forever, or will they one day collide? Or will some fly off, killing us all? You can see why it was a question of interest. The winner of the competition would be awarded 2,500 crowns and academic fame. The interest in this question actually goes beyond just wondering if humanity would die a horrible death. It was mathematically significant. For over 200 years, brilliant mathematicians had tried and failed to answer it. Why? Well, why don't we ask the first guy who ever made a serious attempt? Newton. Imagine it's 1687. Isaac Newton has just changed the world with his three laws of motion and the universal law of gravitation. He'd unlocked the universe's underlying principles, offering a blueprint that explained everything from the falling of an apple to the orbits of planets. They were the perfect tools to solve the solar system problem. He could figure out the equations that governed the motion of the planets, solve them, and the solutions would tell him how they moved for all time. This was actually a fatal question to Newton. He was a devout Christian, so to him, the solar system was only around 6,000 years old. This timeline was far from guaranteeing it would orbit peacefully for the next 1,000 years too. The logical thing to do was start with just two bodies, figure out if they were stable, and then just keep adding more bodies, one by one, and repeating the process. Newton's laws worked remarkably well for the two-body problem, and he quickly found that it was stable. It was when he added a third body that things took a turn. Newton couldn't figure it out. Not only could he not solve the equations, he couldn't even figure out what the equations of motion were. He wrote to his friend Edmund Halley, "No problem has ever made my head ache like the problem of the Earth, Moon, and Sun." This was deeply disturbing, not just for the stability of the solar system, but for all of physics at the time. Newton's laws had ushered in an age of hope, a new understanding of our universe where every force and effect seemed predictable. His laws solidified the idea of determinism, that the present state determines the future state. Physics had basically been reduced to a roadmap. The physical laws told us the shape of the road, and the initial conditions told us where we were. Just plug in the numbers, solve the equations, and we could predict the exact location that we would be at some future point. Place the car in the same lane, and it would always end up at the same destination. Start a planet at the same point, with the same velocity, with the same forces acting on it, and you could predict its exact location at any future time. At the heart of Newton's determinism were analytical solutions, exact mathematical expressions that give rise to exact numerical results. Analytical solutions are still all the rage today. If you've ever solved a physics problem in high school, chances are it was an analytical solution. There was one caveat to all of this optimism. We could never know the exact conditions of anything to 100% precision. Measurements of position and momentum would inevitably be slightly off, even if it was imperceptible to our senses. And of course, we now know about quantum mechanics and the Heisenberg uncertainty principle, which says that it's impossible to simultaneously know the position and momentum of a particle with perfect precision. But there was also the belief that that didn't matter, that given approximate knowledge of a system's initial conditions, we could calculate the approximate future conditions. Small errors in measurement would lead to small errors in predictability. This belief was well justified. A tiny error in the position of Comet Halley in 1910 would only cause a tiny error in predicting its arrival in 1986. It was thought that all there was left to do in science was measure things more accurately, have a better understanding of the laws of physics, and get more computational power to carry out computations. Then, all the future would lay open before our eyes. So with all of this hope going on, it was a pretty big blow when Newton couldn't figure out the motion of just 3 planetary bodies. It questioned the foundation of deterministic predictability, an idea that he had inspired. This was the first hint that this rosy picture wasn't quite right, which brings us back to King Oscar's maths competition. More than 200 years had passed since Newton, and with it, many new mathematical advances. The time was ripe to give the old solar system problem another crack. A mathematician named Henri Poincaré rose to the challenge. Now, I'm way too Aussie to say that without offending some French people, so I'm going to get my French husband to say it. He started with the 3-body problem as well. He looked at an even simpler version actually, 2 larger masses fixed in place and a third massless body which was affected by their gravitational pulls. He limited the problem to just figuring out the motion of this smaller massless body, how it was affected by the 2 larger masses. Like every mathematician before him, Poincaré couldn't figure out the equations. But unlike any mathematician before him, he didn't let that stop him. He just invented a new way to do physics. Newton's method zeroed in on individual scenarios, but Poincaré wanted to zoom out and see the bigger picture. If Newton's laws showed us the road, Poincaré wanted to study the entire map, understanding the overall behavior and patterns within the system as a whole. And what he saw was the key to cracking the 3-body problem. To understand what he saw, we need to get familiar with fixed points. Take a ball rolling on some hills. There are 2 points where the ball can come to a natural stop, here and here. These are called fixed points. But there's a very important difference in the nature of these fixed points. With this one in the valley, if we give the ball a slight nudge, it will be drawn back to the fixed point. We call this a stable fixed point, and they act as attractors in the system. Objects near them will be naturally drawn to them and they'll tend to stay there. But at this fixed point, if we give the ball just a slight nudge, it rolls away fast. This is called an unstable fixed point. They have a repelling nature. An object in their vicinity will be repelled away. Poincaré found that the interaction of the gravitational forces can create these fixed points in space. Points where the forces are perfectly balanced, so that an object is either drawn in to hang out there or repelled away. But then he found a third kind of fixed point with a bizarre property. Fixed points that were stable and unstable at the same time, attracting and repelling. How is this possible? Well, look at this seemingly stable fixed point. Now let's make it 3D. Oh! The ball is naturally attracted to the fixed point, like it's stable. But the slightest nudge can send it rolling down either side, like it's unstable. These are called saddle points. And what's interesting about saddle points is that the tiniest difference in the position of the ball can send it rolling down either side. Contrast this to the Newtonian way of looking at things, where slight inaccuracies in measurement lead to slight inaccuracies in the predicted trajectory. A slight inaccuracy in a saddle point can lead to a totally different, unrecognizable trajectory. These saddle points are the seeds of what would later become known as chaos. Poincaré saw that the gravitational interactions between the 3 bodies create these saddle points in space, extremely sensitive spots that attract objects in only to send them off wildly in one direction or another. And the slightest difference in position, force, or velocity can catapult them into drastically different trajectories. This is called extreme sensitivity to initial conditions. Now make no mistake, this behavior isn't random. It's 100% deterministic. It's just not predictable. It's like Poincaré discovered intersections in our roadmap. If a car starts in the same lane, it'll still end up at the same destination every time. But if it starts in just the next lane, it'll end up somewhere completely different. You might be thinking, but surely that's not fundamentally unpredictable. If we make better measuring devices, we can accurately determine which lane we're in. But in reality, these lanes are infinitely thin trajectories in a continuous space, and there are infinitely many of them. In practice, it's impossible to measure exactly which trajectory we're on, not only because of Heisenberg's uncertainty principle, but also because tiny disturbances miles away can impact the position and velocity of a body. A slight gravitational tug from a distant moon or the solar wind's subtle push. In practice, we can't measure every single tiny movement and force in the universe. We can only measure about which trajectory we're on, which, as you can see, doesn't help us for long-term behavior. Poincaré's discovery of chaos broke the Newtonian view of a predictable universe, opening up a realm where predictability is limited not by our technologies or methods of calculation, but by the fundamental nature of the universe itself. Now, you might think that being such a revolutionary idea, this is where chaos took off. But actually, nobody understood what Poincaré did because he was so bad at drawing. He even got a 0 on the entrance exam for college on the mechanical drawing part. So that was quite unfortunate, and chaos theory didn't take off until the 1960s when it was rediscovered by this guy. But Poincaré did win the King's Maths competition. Rather than solving the three-body problem, he proved that it is analytically unsolvable. But wait, you say, what about all of these articles claiming that there are solutions, or all of these videos explaining the solutions? If the three-body problem is unsolvable, what are they talking about? Well, they generally mean one of two things. It's true that we can't solve the three-body problem with a neat mathematical formula that works for any scenario. In other words, there is no general solution to the three-body problem. But mathematicians have solved it for some specific cases, like when the bodies form an equilateral triangle, or a stable figure-8 pattern, or for some periodic orbits, orbits that repeat over and over indefinitely. The other thing a solution can mean is a very good approximation. In the absence of a general analytical solution, scientists still wanted to be able to predict the orbit of three bodies, so they developed a technique called numerical integration. It works by breaking the problem down into smaller time steps. For each time step, the gravitational forces between each pair of bodies are calculated. Using the forces and the current velocities, an algorithm updates the velocities and positions of each body for the next time step. This process is repeated over and over, progressively calculating the trajectory of each body. With today's computing power, numerical integration is extremely effective. 300 years after Newton, the three-body problem continues to teach us about our world. Poincaré's geometric techniques not only allow us to solve problems that Newton's old-school methods couldn't, but they also birthed chaos theory and the field of nonlinear dynamics. These tools have revealed chaotic systems across a diverse array of fields, from weather patterns and ocean currents to the rhythm of the human heart and the stock market. Chaos is everywhere. It's fascinating how even systems governed by precise laws can behave in ways that are fundamentally unpredictable. What I find super inspiring about this story is how Poincaré cracked the three-body problem by looking at it a different way. I've always been fascinated by the way scientists and mathematicians think. A lot of you don't know this about me, but I actually started out doing a biology degree before I switched to physics. I loved biology, but I felt like I was learning things, whereas in physics I was learning a totally new way of thinking. How to reason about our world, how to think logically, how to solve problems most effectively. I thought, what could be more mind-expanding than a totally new way of thinking? Have you ever wanted to learn to think more scientifically? If the answer is yes, let me introduce you to today's sponsor, Brilliant. Brilliant is an interactive website and app that focuses on learning by doing. It has thousands of lessons in math, data analysis, programming, and AI. What I love about Brilliant is 1, their first principles approach to concepts, and 2, their strong focus on problem solving. The first principles approach builds your understanding from the ground up, so you're not just memorizing, you're actually developing your own intuition. And the problem solving is not only fun, but it reinforces what you've learned, being proven to be 6 times more effective than watching video lectures. I've been using Brilliant for years now, and while I've learned a lot of new things, what I've noticed most is that my critical thinking has improved. I might not be as cool as Poincaré, but we can all head in that direction. Whether you're a student, a professional, or just a curious mind, understanding the fundamentals of scientific thinking can transform the way you approach problems, not just in science, but in everyday life. To get started, I recommend this course, Scientific Thinking, where you'll learn the scientific principles behind everyday experiences. Brilliant's bite-sized lessons make building a daily learning habit easy, and just 10 minutes a day can make a big difference. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/atom or click the link in the description. You'll also get 20% off an annual premium subscription. Thanks, and I'll see you in the next episode. Bye!